Our first talk this afternoon is from Professor Hanadi Rafai, Water, Water Everywhere and Lots of Drops to Drink, the Rime of the Future Engineer. I love that title. Dr. Rafai is the Moores Professor of Civil and Environmental Engineering at the University of Houston. She directs the Hurricane Resilience Research Institute, a Gulf Coast multi-university collaborative center focusing on resilience to severe events and natural disasters. Dr. Rafai is a water engineer with extensive expertise and experience in water quantity and quality in natural water systems and the cascading impacts of severe events and natural hazards on industrial and environmental infrastructure and human and ecosystem health.
Okay, so thank you very much for being here tonight and for inviting me to speak. And I wanted to talk about one of my favorite topics, which is water. However, unlike the rime of the ancient mariner, where they were surrounded by seawater, but not a drop to drink, we're going to talk about ways where the rime of the future engineer will ensure that we have ample drops to drink. So thanks again for being here. Now, from the beginning of time, people recognized the importance of water, and they worked really hard to actually transport it from faraway places so they could use it. So the earliest systems, known as the qanats, the Persian qanats, they were really marvels in engineering. They were able to transport water. They tapped alluvial aquifers, and they were able to transport water over many miles and many different systems within their environments. They built these underground tunnels and pushed water by gravity. Now, in a very recent paper, they talked about this whole concept of diffusion of knowledge. Back then, they did not have social media, and they did not have LinkedIn. They did not have any of the technologies we have today by which we share information. However, somehow they were able, that knowledge about water diffused to many societies around the world. So we see some of these things. I'm going to try to use this fancy tool, diffusing from Persia to literally everywhere in the world: Jordan and Syria, Spain, the Americas, Morocco, Arabia, North Africa, all the way to Afghanistan and Pakistan and China. And these names in italics are the names of what they call their technologies, their water systems. So pretty amazing, this diffusion of knowledge. So folks like the Greeks built on what the Romans did, and they gave us really a very important technology, which is siphons. And siphons are tubes that connect these two bodies of liquid, allow the liquid to flow upwards. I mean, imagine that way back when they didn't have tools to do much of this stuff, but they figured this out. And of course, the Romans refurbished and expanded a lot of the technologies, the aqueducts that were built by the Greeks. And so the one in Constantinople is one of the most famous ones. It's more than 300 kilometers long and brings water from 100-kilometer distance. So pretty amazing marvels in engineering. Now, this didn't stop there. We see that innovation and ingenuity in Mesopotamia and their irrigation canals, really pretty fascinating. We see it in the way that the Egyptians handled floods in the Nile and used it to actually irrigate and grow crops in a very arid region. We see it in technology that they developed, that this shadoof is the idea that you can haul water from one place to the other using what we now have more fancy names for. And then you'll see the Nilometer, which is really a stage that measures water levels, like the ones you see under the freeways where we have flooding. They had that way back when, a long time ago. And then you'll see the Mayans, they had the first filtration systems, believe it or not. And you'll see the Indus had advanced urban and water and wastewater engineering. So we're building on this great legacy, right, of folks that have come before us. Now we fast forward and look at what's happening in the United States and in modern times. And what you will see is that it took us a while, till 1872, to have the first filtration water treatment plant in Poughkeepsie, New York. And then beyond that, what motivated a lot of the water systems we work with today are the diseases and recognition that water is a carrier of disease unless it's treated and maintained and clean. So you'll see that chlorination began in about the 1900s, I would say. And as a result, of course, the deaths that came from all of these diseases started declining. Now, the issue then became wastewater, and Britain led the world with their technology. They really did that because of all of the pandemics and the amazing, I guess, outbreaks of diseases that decimated much of their population. So they gave us a lot of inventions, among them spreading wastewater on land application, intermittent filtration, septic tanks, and basically trickling filters, which you see here on the right are some of the things that they brought. Now, the thing is, today we are at the cusp of having to change the conversation about water. What we're doing and have done to date is not going to serve us and is not going to work into the future. And I'll tell you why, but I'll tell you how we can get over that, right? And so first, we're going to talk about where water comes from. Believe it or not, a lot of folks really don't have a good handle on where water comes from. And then we're going to talk about how we design water systems today and why that is challenging to continue doing that into the future. I'll present a little bit about the Texas water story because we live in Texas. I live in Texas. I care about Texas and its water. And then we'll look at water from a different perspective, from the economic perspective. We then talk about desalination, perhaps in my mind, an unescapable water future for most of the globe. And then we'll really make the case for the nexus of water and energy and productivity and water as the way that is going to be the rhyme of the future engineer, where we have to be inventive and we have to have the resources to get the job done, which is ensuring clean and safe water for everyone. So natural and unconventional water sources. We have surface water, rivers, streams, lakes, etc. We have groundwater, which we've depleted a lot of them, aquifers, wells, and springs. Rainwater, that's where most water comes from, glaciers and snowmelt. Now, recently, we began exploring what I like to call unconventional water sources, and these are going to be recycling it, reusing the water that we've used before. There's technologies to grab water from fog and humidity. You'll hear about produced water today, so I won't comment on that, provided your speaker shows up, right? And then lastly, we're going to talk about seawater and the opportunities it presents. Here's what we do to water today, right? Looks great. Lots of work for engineers. So we start with a water source, usually a surface water. We pull it out with an intake structure, and then we process it through these umpteen technologies that are really quite heavy in engineering and technology, heavy on energy to run the water through them. And then we have distribution and storage, really complex networks. When we're done with all that water, we take all that back and put it in a wastewater treatment system, which is just as complicated, right? And the outcome from all of that is that the wastewater that's been treated is discharged to rivers and streams. However, notice on the right, with the top right, below the top picture, there's waste that's being generated, and the same happens with wastewater. We generate sludge, and that becomes biosolids. The biosolids are spread on agricultural lands. So if the biosolids are polluted, then your food sources also have some of that pollution and could be harmful to humans. So what is the issue with the current conventional water delivery model? From a technological standpoint, it's energy intensive. It consumes a lot of chemicals. It's ineffective for some pollutants like PFAS and rubber from tires. I'll talk about that a little bit. And we, as you know, have deteriorating infrastructure, and the wastes that are generated are an issue that we have to deal with. So then other challenges that come with our systems are even more pervasive because in times of water deficit, who gets to be first in line, right? There are many users of this water: agriculture, industry, municipal, commercial, the energy sector, environmental, recreational, right? So who has first in line? And then beyond that, who's going to pay for new water sources? And how are we going to deal with emerging water users, mega users like data centers, which you will also hear about today? Now, some of the things we need to think about, be proactive, is should we consider sharing water or transferring water rights or transferring water from one place to the next? And how would that work? Do you have the have and have nots? And how do you kind of make that determination? What to do when you have too much or not enough? These are the extremes of drought or extreme rainfall or hurricanes, whatever have you. And then is it likely that we can conserve enough to actually meet the demands? Is it likely that we can harvest from these really distributed sources like rainwater? What would incentivize people to do that? And then what about infrastructure retrofits to reduce water losses and conservation? How do we pay for all of that? So that's what I'd like to talk about today, given that you are seeing these titles in headlines in the news almost every day. Wouldn't you agree, Louis, that this is from Microsoft? They pledged to save water. In the AI era, they expect water use to soar. So I want to emphasize that we moved from the agricultural to the industrial, and now we're in the compute era. And the story has changed and has to change because we will not be able to meet the demands. So the Texas water story, we either have too much of it or not enough. And where we have it is not where you need it. So that becomes a challenge to kind of deal with that. These maps are pretty interesting. They're from a Texas Water Development Board. The important one is down here on, boy, this thing is interesting. The one down here shows you the rainfall over Texas. So you get a lot more rain on the east side of Texas, border with Louisiana, the coast. But then as you go to the Panhandle, West Texas, it's much less water. And then we have droughts, we have extreme heat. I'm not even showing 23 to 25, which is the hottest years on record so far for Texas. We have flooding. This is just an image of the flooding in Kirk County. This is a map of all of the natural hazards that hit Texas, from droughts to extreme rain, hurricanes, fires, whatever have you. This is a disaster declaration count for Texas. So all of these things bring to mind that Texas, we have a problem. Right? So you'll see on the lower right are the projected or existing data centers for Texas. There's more than 400 of them. Half of those already exist in a variety of different shapes and form, and the rest of them are proposed or planned. So we're going to be one of those data hub thingies like Virginia. And what I want to bring to your attention is the Texas Water Development Board divides Texas into all these regions, right? And I already showed you the rainfall map. So we may have a lot of water on the east and the Gulf, but a lot of these centers are actually in West Texas and in the Panhandle, in areas where we are competing with industry for water to generate oil and gas, right? So something's got to give. And unfortunately, two strikes for data centers, according to a new report that came from Bluefield Research. Their theory is, their data demonstrates that the issue is not just the water use, but it's the power plants that are going to use more water to provide the energy for the data center. So that's where the two strikes come in, right? So they're having to build power plants, get water for those, and they're having to use the water to cool the machines that are in, the data centers. So two strikes for data centers that they're going to have to address, and this is real data from that report. It's online. You can look it up and read the report. It's pretty interesting. So in the US in general, what have we done? Well, we've had 125 years of US water spending. We've not been sitting idle. We have been paying for systems, right? But the thing to understand is the pricing of water needs to be better understood, and we need to price it right because it is the resource of the future. Now, I'm giving here some examples. I'm not going to go into them in detail, but I get water from the city of Houston. I pay maybe about 5 or 10 cents a gallon on a good day. Now, if I use a lot of water in the summer, that number jumps up, right? But this is a gallon of distilled water that you buy from the store. You'll pay $1 to $2.50 for that gallon of distilled water. And the reason it's expensive is the cost of the amount of gas that goes to make that distillation system work. And it's 0.15 gallon of gasoline equivalent in BTUs is needed to generate that gallon of distilled water. The rest of the cost is in the plastic and trucking this gallon of water all over and selling it, and people have to make money along the way. Now, what's interesting is in comparison, the price of gasoline, well, not today, I haven't filled up yet. At least it was last week, $3.10. I'm not sure what it's like today. But the point that I'm trying to make is that we spend about $1,200 per capita in the US and on water. 2.2 billion do not have safe water. 40% of the world will face water stress by the year 2050. We need to price water right in order to get beyond where we are today, where there are these dichotomies in pricing, and we'll explain why. So what drove the cost up over time? And this is a chart showing from the 1900s to 2025 how much water per capita the US has spent. And essentially, dam building, that was our biggest technology, right? We built a lot of dams and canals in the 1900 to 1950. Then from the 50s to the 80s, we started recognizing the importance of urban networks and building those. That drove the cost up. Then we had environmental people like myself insist that we have no silent springs and get clean water. That added to the cost, ensuring safe drinking water act. And then today we find ourselves with aging infrastructure, with compounds like forever chemicals, PFAS and lead, and they have to be removed and they have to be treated. So that's driving the cost up to $1,200 per capita. However, the problem is that water access has also changed over time, and that's part of this cost model. And I'll move quickly through these slides, but the well and the ditch era basically had to dig a well to get water and pull the water out, essentially back in the early 1900s. Then we had the great dam building era that I mentioned, and you're looking here at the multiplier in real terms of how much that increased the cost of delivering water, having access to water. And then we got into the regulation and treatment era in the 2000s. And this is the really scary part, that the US needs about $3.4 trillion in water infrastructure over the next 20 years to meet the needs and the demands. And the even scarier part is that the federal share is almost no more than 8% of that, and the rest of the money is borne by states and local government. And so the difficulty or the challenge that we find today is you need to spend a lot more than $1,200 per capita. Somehow those funds have to be found. So the key takeaways, we have a big infrastructure gap and our pipes are aging. We are spending far less than what we should spend to ensure safe and clean water deliveries. Now, water demand is relentless. The fact is that it keeps increasing. We have population growth, have urbanization and industry. We're going, as I said, from farming to manufacturing to information technology. So the water demand per capita is going way up. For factories, plants, cooling system, they all require water. And then data centers and AI, the digital economy, we call it water hungry. And one data center can consume about 3 to 5 million gallons per day. A family of four typically would use about 5,000 gallons a month. So you could see, you can kind of think about the equivalent number of people that are replaced by the need for that data center. And then we have more coming with AI and quantum computing. They're accelerating those needs. Now we have stressed natural sources. We've depleted a lot of the streams and rivers and groundwater aquifers. And unfortunately, we're all, facing issues like drought and other risks that are affecting those sources. In addition, legal frameworks are lagging behind physical reality. So in Texas, you cannot transfer water across watersheds. You can borrow water. Houston borrows water from the Trinity, for example, but you can't transfer that, water from Houston somewhere else. And then we do have opportunity sources, and that's where we need to think about those pretty carefully. Rainwater harvesting is underutilized, and there's not a way to convince people to do it if you don't incentivize it, kind of like using solar and wind and other technologies. Glacial snow melt is seasonal, but it's not captured at scale. We have technology to collect water from fog and humidity, and at least in my humble opinion, seawater may be our largest untapped resource that could help us out in the long term. Now, the good news is not everything we do is bad. Current technologies the current water distribution model is not a bad one. It does have issues that come with it that we need to resolve. Emerging contaminant crisis. Now, we went from infectious disease, we handled those, dechlorination and all that, but now we have these emerging contaminants that are quite problematic. So PFAS are forever chemicals. They're literally everywhere and in everything. So pretty hard to get a handle on those. Microplastics are in the same domain. And then lastly, the new emerging, I call it the new kid chemical on the block, X6-BPD quinone, that comes from tires shedding rubber, and they're added to tires to make them last longer and maintain their properties. And unfortunately, they shed. And this compound is totally toxic to salmon and other aquatic life. And so right now, a lot of research is going on to see what we could do about this compound. Now, wastewater, on the other hand, the good news is it went from being sort of a nuisance thing to becoming an intelligence asset. So we've done a lot to identify disease in wastewater effluent from communities so we can preempt any kind of outbreak. COVID is one of those, but now we're looking at the flu, RSV. We can monitor, and of course, privacy notwithstanding, we're not addressing that today. Opioid use, antibiotic resistance, and illicit drugs, you can monitor that at the population scale. And then you will find that these systems are now early warning systems. The CDC and the World Health Organization, they're really expanding their wastewater surveillance networks globally. Now, expanding supply without new sources, is that possible? Well, we're trying everything. So we're looking at recycling and reclaiming water. We're looking at capturing stormwater and trying to do something with it. We are looking at produced water. One of my student teams won the Texas Water Challenge several years back. They proposed treating produced water. And we can improve conservation. We can separate our systems where you have gray water, like your kitchen water, separated from bathroom water, and that gray water may be a good reuse opportunity and infrastructure rehab. However, let's take a look at what Texas is up to, right? So this is all data from the Texas Water Development Board, all available online. On the top right, they're showing where we are today and what is the gap that we will face in 2070. So the red is how much more water we need, and the green is the idea that these would be strategy supplies. So this is new water that we have to come up with to meet that red bar. So over there on the top left is a map of all of the reuse potential of wastewater. If we're going to take all that wastewater and reuse it, that's how much we have to work with. And then next to that is this whole technology of managed aquifer recharge. Some of you may have heard of it, but basically you're trying to reintroduce water from rain or storm water or treated water. You reintroduce it and replenish these aquifers so that it's stored, and when you need it, you can pump it back. And this shows the few dots are the few places where they're doing actual testing of some of these technologies. On the left is the TWDD assessment of the potential that you would gain from harvesting rainwater. In here, and this map is dated, it's actually from 2019, I'm not sure it's reflective, but basically it shows the areas with the volumes of produced water that they generate. And then lastly, we can build reservoirs, but they take forever to build. In Texas, we have maybe 1 or 2 natural lakes that are still built by us. And unfortunately, this map actually shows the deficits from the current drought that we're having. So all the reservoirs in the red have already lost sufficient volume of the water that's in them. So that's the issue with reservoirs, that if this drought continues, all the blues will also turn into reds. And that creates a significant problem for all of us. So Texas is exploring all those options, but my guess would be it's not going to be enough. So seawater, the world's largest water reserve. most of the earth, as you know, is seawater. And there are things that really support looking at desalination, right? Unlimited supply is right there. It's literally free, right? Technology costs are declining. Then we do have the location advantage in the sense that many people are moving to coastal areas because they have temperate climates and climate independent. The ocean is not going to dry up when we have a drought. There's always be water, right? Now, where we have some of these technologies right now is not very expensive. This is showing some of the places where they've already embraced desalination in Saudi Arabia, Gulf states, Israel, the United States, Spain, and Mediterranean, China, and Australia. And they have their primary drivers are different, but essentially that's why they're investing in desalination. So in the future, migration due to climate extremes are going to concentrate populations along the coast. And therefore, if we're going to meet the needs, we may have to basically go towards more desalination in almost every country in the globe. Now, the core challenges with desalination, it's not an easy lift. Energy cost, time to implement, climate variability, and delivering it where needed. So we haven't surmounted those challenges, but we can address some of the needs, at least of the coastal areas that I mentioned earlier. So this brings me to the rhyme of the future engineer. And the rhyme of the future engineer is connecting water and energy system, because without doing that, we would not be actually able to achieve our goal. And how we do that is we use water to make energy, and we use energy to treat water. And that symbiotic relationship has to be built and has to be part of every new systems or retrofits or ideas that we think about. I'm working with students on hydropower because that's really the most likely, large source of energy generation using water, and it's historically been used forever. We're looking at in conduit power. When you move water from high places to low places, we try to depressurize the system so that the pipes don't blow up. Maybe we can grab some of that pressure differential and turn it using a turbine into energy. It is possible and it's doable. And the system already exists. So it's not a retrofit, it's an add-on. We're looking with students at marine energy technologies to generate energy, and then osmotic power. And a paper just came out. It's about floating droplet electricity generators. So this is as opposed to having basically you can generate power from raindrops is the synthesis of on the other hand, we need energy for treating water. However, we have to be clever about where the energy sources are coming from. So we might go to solar powering desalination plants. We might be able to reclaim cooling water from power plants, electrolysis for water recovery, and heat-driven atmospheric water harvesting. So this one down there, instead of being photovoltaic, is basically hydrovoltaic. That's the technology. And as I said, the paper just came out on that. Pretty interesting. So data centers, the challenge, they use a lot of water. I didn't know that training one large AI model will use 700,000 liters of water. That's pretty astounding. It's a lot of water. And so the global data center water will increase by 2030, triple. And most of these data centers are sited based on energy cost, not water availability, and that's creating all kinds of problems. Now, the opportunity is to co-locate them perhaps with desal plants and power them with ocean wind, return treated water as fresh water, et cetera, recovering waste heat, many different ways we can think about where we capture the opportunity with these data centers. And then if we're going to build them, maybe think about building campuses relying on circular economies, where we combine data centers with renewables and water treatment technology. Wealth enables water and water technology. As you know, emerging nations or developing nations, they don't have the resources, so they still are without, sewered water systems. Whereas where you have money, you can actually afford technology. Israel, they're leading in membrane technologies, and they have turned the desert into a lush green garden. And then Libya, the great man-made river. If you've never heard about it, look it online. It's amazing how they, again, pumped water from the groundwater in the desert, carried it to the coastal areas with this really, I call it a ginormous tunnel, basically. Saudi Arabia with mega-scale desalination, and then Singapore, their New Water and Four Taps initiative. So looking ahead to 2055, and I'm almost near the end of my time, so I'm going to go through that quickly. How much we earn will tell us how much water we can afford, basically, into the future. And I'm going to show you or walk you through two scenarios: slow growth, 1% per year. America right now is about 1 to 1.5% growth. With an AI-driven economy, if we can get to 3.5%, that would be awesome. We can afford a lot of water. So how does this work? Well, on average, right now, the individual income is about 60,000, and we have the two scenarios. The low growth will be 85,000 in 2055. The high growth will be 176,000 on average, the income. And if we look at the high growth, we will have excess money generated, enough to fill the gap and pay for all the water for that $3.4 trillion, whatever that number was. I forget how many zeros is a trillion, right? But it's a lot. And so the idea being is we really need to kind of think about how to balance this productivity and economic growth with all of these needs and challenges so that we can actually afford our needs for water and fill that gap. So in addition to the water energy nexus, we need to think about the productivity water nexus, that in a high growth environment, we will be able to pay the $3.4 trillion and have the water systems that we need. But if we don't, we're going to struggle to be able to meet the needs with water. So a brighter future, circular water energy economy. We want to think about integrated planning, distributed systems. Nature-based solutions will help us in a lot of different ways, and digital intelligence, where to me, the monitoring systems for water are kind of ancient technologies. We need to think about much newer sensors and ways to detect leaks, predict demand, and manage complex distributed systems in real time. I'll stop there and leave you with the thought that water security is national security, and the choices we make in the next decade with desal, water reuse, infrastructure investment, and energy integration, they will determine whether the world's growing population will have access to safe and reliable water. Thank you very much.